In high school and in Cal 1 and Cal 2, we often work, or almost exclusively work, with functions that take a number and output another number. By that I mean, for example, consider the function f of x, which is equal to x squared. Right? It can take any number, for example 2, and it will output another number, in this case 4. But f of 3 would be 9, and so on. Okay, f of root of 2 would be 2. So this function in particular, it takes essentially, what does it do? It takes a number, a real number, and it outputs another real number. So this notation I just wrote, it means f is a function that has an input that's part of the real numbers and an output that's also part of the real numbers. But we could have other types of functions. So imagine I have a function that actually takes a point in the plane, maybe 1, 2, and it maps it onto maybe a number. That could be, so that means that where I'm mapping is, I'm initially is over the real line. So I'm taking a number in R2, not a number, I'm taking a point in R2, and I'm mapping that onto a number in R. What kind of function would that be? Well, for example, you could have f has two inputs, right? X and Y. But I can also write that as a single input by putting my two values of x and y inside a vector. So it takes a vector with two coordinates. So in some way it's one input, or you can see it as two inputs. Okay, depends on how you approach it. But it essentially takes two values, right? And I could say, well, the output would be x squared plus y squared. Why not? That's an example. So in this case, 1, 2 would be sent on what? Well, 1, 2 would be sent on 1 squared plus 2 squared, which is 5. So 1, 2 would go onto 5. Okay. So that's an example. So in this case, f, you see, it takes points in R2 and maps it, and look at how the arrows drawn. There's this straight side at one end and just a normal arrow afterwards, and the image is part of the real numbers. Okay, so that's an example, but I could also have maybe 1, 2 not mapped on a number, but mapped onto another point. Why not? So maybe 1, 2 could go on 2, 3, 4. Well, what kind of function would do this? Oops. Well, maybe function called, I don't know, g would take x, y and output x plus 2, y plus 2. That's just an example again. And look what g does to 1, 2. It takes 1, 2 and maps it onto 3, 4. Just like I illustrated above. So in this case, g would take something in R2 and maps it onto R2. In general, I could have a function that takes a point in Rn and maps it to a point in Rm. So I could say point, I could say vectors, okay, because there's this duality point vector. So essentially it takes a point or a vector in a space and maps it onto a point or a vector in another space. Now, I could also, instead of drawing the image separately, since in this case my function maps from R2 to R2, okay, on this picture, I could also maybe just eliminate this, okay, and put 3, 4 here. right? And say that 1, 2 has moved to 3, 4 through my through the through the application, say, of my function. So there's this idea of movement, right? So essentially, my function, it takes this point and whoop, it moves it there. So in linear algebra, we're often want to have functions that convey this idea of movement, and we'll call functions transformation. So transformation in this course will be kind of a synonym for function. So this in mind, we're going to define what's called a linear transformation. But if that word bothers you, just think linear function. So a linear transformation T from Rn to Rm is such that for all u and v in scalar k, so a transformation is a special type of function. It satisfies the following two properties. T of u plus v, so u plus v is the input, is the same as T of u plus T of v. And T of ku is the same as k times T of u. We'll see that this is very restrictive. So I'll give you an example of a linear transformation. So here's a transformation that takes a point in R3 and outputs a point in R2. So this is what my function's like. Okay, what I'll try to show you is that it satisfies the previous two properties and that it's indeed a linear function, a linear transformation. So first thing is if I do T of 1, 2, 3, so if I apply my transformation to 1, 2, 3, following the rule, its first coordinate is x plus y, so 3, and y plus z, the second coordinate, so it's 3, 5. Okay? And let's take a look at maybe another value. It means minus 1, 0, 1. So this is going on to minus 1, 1. Now that's those two values here that I have, that's going to be like my u and that's going to be my v. Okay, so let's take a look at property number let's take a look at property number 1. Let's see if it's satisfied. If I do T of u plus v would be 1, 2, 3 plus minus 1, 0, 1. Right, so that's my input. So what's my input? I'm gonna figure out what that vector is, right? Because I have a sum of two vectors to add, like in my input. So it's gonna be 0, 2, 4. And my output is going to be what? It's going to be not t. My output is going to be x plus y 2, y plus z 6. So 2, 6. Okay. So I've essentially calculated this. Now I'm going to calculate the other side and see if it is equal to the left-hand side. So T of u would be T of 1, 2, 3, and plus T of v, that would be minus 1, 0, 1. Okay, so what would that be equal to? Well, T of 1, 2, 3, I've calculated that. That's 3, 5. T of minus 1, 0, 1, that's minus 1, 1. Now let's add those two. I get 3 minus 1, 2. 5 plus 1, 6. You see, they are equal. So property number 1 works. If I look at property number 2, I'm going to choose, just to illustrate, k, maybe k equals 2. Okay, so I'm going to calculate this side right now. So T of 2u. I'm going to calculate 2u first, right? 2u is 2, 4, 6. I'm going to apply my the rule for linear transformation. So first coordinate is x plus y, so that's 2 plus 4, 6. Second coordinate is y plus z, so 4 plus 6, 10. Now I'm going to calculate the other side here, k times tu, and see if they are equal. So k, so 2 times u. Let's calculate this. This is 2 times t of 1, 2, 3. I know that what that is. That's 3, 5. 2 times 3, 5. 6, 10. And once again, those two are equal. Okay, so we see that t here is really a linear transformation according to my definition. So of course the big question is, what type of functions are linear transformation? So we'll answer that a bit later. First thing is, I want to show you a few things about linear transformation. They're quite neat in some way. They're neat in the way that if I know two function values, I'm good. Okay, two special function values. It's actually going to be enough information to calculate function values for all other numbers. It's like me telling you, I've got this function. I know that f of 1 is 3, f of 5 is 6, and from this I'd be able to actually find the function values for any other number. Now you'll understand that for most functions that's not true, right? If I just give you two values, that's not enough to figure out what the other numbers are, right? If the graph is a line, that's okay, but if a graph is a parabola, that's not okay, right? If I give you two function values, it's like giving you 2 points in the plane. There are many parabolas, right, that would actually go through these 2 points. On the other hand, there's only one line going through these 2 points. So giving you two function values, if I'm not telling you what type of function you're dealing with, you won't be able to find it. But if I'm telling you it's a linear transformation or a linear function, you can. Just like I could with my line. So note, number one, if I've got a vector u, okay, and I can write it in terms of I and j, right? Remember what I and j are? I and j are, so let's say we work in R2, it's 0, 1, and this is, 1, 0, and 0, 1. So that would make my vector the vector AB essentially. So I can decompose it as AI plus BJ. Or graphically, if you prefer, I've got this vector U here. This is A, this is B. Well, the idea is that to get to U, I do, so I would be this, right? So I do A times I, which gets me here. And maybe j is this vector, and if I do b times j, it gets me there. So overall, by doing this plus this, I'm getting to u, right? So if u is this, the cool thing about linear transformation is I only need to know how I and j are mapped by my linear transformation to know where u is mapped. So I'm going to write this down. So this is what I wrote. So if, how u gets transformed or mapped depends on how I and j get transformed. So maybe I'll show you an example. Suppose I have, I know that I, right, which is the vector 1, 0. Suppose that it's equal to, I'm actually it's gonna help us later on. I'm gonna put my vectors in column format. So this is 1, 0, and it gets mapped onto 1 minus 2. And suppose I know that j, which is the vector 0, 1, it gets mapped onto 3, 0. Okay. And t is a linear transformation, which means that I can use properties number 1 and 2. Okay, it obeys these rules. Let's take a look at t of some, I'm going to choose some random point, right? Minus 1, 2. Okay, where is that going? Well, minus 1, 2, I'm going to decompose it using this. Okay, I'm going to write it as a linear combination of I and j. So this is t of, it's minus I, right? Plus 2j. All right. So that's, so the way we can see this is that it's, this is kind of like, so I know I've used u above. Okay, but I'm still going to use u. So u here is not the same u as the one I of course highlighted in orange. Okay, so I've got a sum. Essentially, I've got a sum of two vectors. Okay, and what I know is that using property number one. Property number one is what? It tells me that t of u plus v is t of u plus t of v. So I'm going to apply this. I'm going to split my linear transformation as the sum of two linear transformation, as the sum of two outputs of my linear transformation. That's better. And minus, sorry about that, we're back. Now, this guy here, I can see this as k times some vector, right? Where k is minus 1. It's minus 1 times the vector I. This is also k times some vector, where k here is 2. So now I'm going to apply property number 2. Property number 2 tells me what? Tells me that t of a multiple of u is that k times u. So I can actually pull out the k out of the bracket. So here, I can take away the minus 1, right? Outside of the bracket. So this is t of I plus 2 times t of j. So that's because t is a linear transformation. I can use properties number 1 and 2. So I see now that actually I can compute what the output of the point minus 1, 2 is, because I know what the output of I and j are. So minus t of I is what? It's 1 minus 2, right? So because this is the example I've created. T of j is 3, 0. So plus 2 times 3, 0. So my point is I can actually, so if I add this up, what do I get? I'm going to get what? I'm going to, okay, so there's something I want to do here. I'm going to bring the minus 1, right? This minus 1 inside here. So it's minus 1 times 1, minus 1 times minus 2. And I'll do the same with the 2. So it's 2 times 3, 2 times 0. And when I add the vectors, I'm going to get minus 1, 1 plus 2 times 3. And here minus 1 times minus 2 plus 2 times 0. So of course I could calculate what this is all equal to. So over here this is 5 and this is 2 here. But my point is that right now I can calculate t of any, right? I chose minus 1, 2 here, but I could have chosen anything here. It would just affect these coefficients. And from this, right, it would affect these coefficients. But since I know what t of I and t of j are, I totally know what the output is going to be if I just know t of I and t of j. So just the function evaluated at two points, or two vectors, I and j. So I can do this in general if I know so more generally speaking, if I have t of u, I just write my u as ai plus bj, and using properties number 1 and 2, I can write that as t of I plus bt of j. Okay, and that's going to be true for any linear transformation. By just knowing what t of I and t of j are, I can know what t of any vector is. Okay, that's what I've illustrated above. So let me write this in, I want to show you in vector form. So if I've got t of, so I'm gonna do the example above with some arbitrary vector here, xy. Okay, so if I've got t of xy, what is that going to be? That's going to be t of x times I plus y times j. So that's going to be x t of I plus y t of j. And for my example, t of I is, what was t of I? It's 1 minus 2. Okay. Of course, that's just for our example. 1 minus 2. And j is 3, 0. Okay. And I'm going to do what I just did here. I'm going to add them up, but keep them in this kind of format that you see here. Okay. I'm not going to evaluate everything. Well, I can't anyway because I don't know what x and y are. So this is going to give me the vector. How am I going to write this? 1 times x, right, plus 3 times y. And over here, minus 2 times x plus 0 times y. Okay. And what we see here is that in each case, hey, what do we have? We've got x plus 3y. That's a linear expression, right? And minus 2x plus 0y, that's also a linear expression. So I've got linear expressions here. Okay, it's not a coincidence. So essentially, the output of a linear transformation will give you a vector where the coordinates are linear expressions. Okay. So what's kind of neat, like I said, is that we only need to know what t of I and t of j are. So see this. These are really the important stuff, right? That we need to remember, right? In order to calculate the linear transformation for any point. So what we'll like to do is write this using this special notation. Okay, so this is a notation we're going to use. Okay, we're going to put these two vectors into one single matrix. So each column will be where respectively where I and j are mapped, and we will say that we're multiplying this by the vector xy. So this expression we have here will be used to define what a matrix times a vector is equal to. So this idea of linear transformation is going to explain a lot more how we actually multiply matrices together. So first thing we look at is the case where we multiply a matrix times a vector. So I'm going to write that down. So we define the matrix vector product between the matrix ABCD and XY. Right now I'm using matrices of that are respectively here 2 by 2 and 2 by 1, but I could have matrices of other size. Okay, but we're going to start with something simple. As A, B, C, D, X, Y. Okay, so this is how we write down our product, right? Don't put anything in between because it's understood that there's a product in between this matrix and this vector. And that's going to be AX plus BY and CX plus DY for the two entries of the resulting vector. Okay, so the idea is that if you look at our previous example, right, this is like AX plus BY, this is CX plus DY. Okay, and if I look at this here and this here, okay, those columns, like I said, this is where T of I is mapped, this is where T of J is mapped. Okay, and the other interesting thing is this part here. You see, I can right there, what I did here, right? The matrix vector product can be written as a linear combination of the two columns of my matrix. So I'll write that down. So the matrix vector product can be written as a linear combination of the columns of the matrix. So I'm going to try to illustrate this here. So here we're looking at this part here, right there, right? So it's going to be, if I have A, B, C, D times X, Y. Another way to look at this is we're doing X times the first column plus Y times the second column. And of course, if you add these two, right, you're going to get back this. So it's basically a different way of looking at our matrix vector product. So here's another example. So the matrix 1, 4, 8, 2 times the vector 6, 9. So applying our definition, okay, we're going to get a vector of length 2. And this, how do we get the first entry? This multiplies this multiplies that, and we add them up. Okay, so maybe I'm going to write this slowly here. So this is going to be 1 plus 6 plus 1 times 6, sorry, plus 4 times 9. And that will give us, what, 36 plus 6, 42. And for the other entry, I'm going to multiply 8 with 6 and 2 with 9 and add those up. So 8 times 2 plus 2 times 9, that gives me what, 18 plus 16, so that's 34. Oh, small typo. I wrote 8 times 2, but it's actually 8 times 6 here, right? As we saw here, 8 times 6. So that's 48 plus 18, so 66. Okay, and like I wrote in the note, you could actually do this by instead doing a linear combination of your vectors. You could say it's 6 times the first column plus 9 times the second column. That's also possible. It will give you exactly the same result. Or you can do it this way. Now here's another example. Can do this too with matrices of other size. So maybe I have 1, 2, 0, minus 1, 3, 6, and multiplying. Now, how does the multiplication work, right? I'm going to make a linear, well, maybe it's the easiest way to look at it. I'm going to do a linear combination of these two columns, right? So I can only have 2 entries here. So we can see actually that if I have got a vector with 3 entries, this matrix vector product won't make sense anymore according to my definition. So I really need still 2 inputs here. So I could multiply it by 2n minus 1. Okay, and how would that work? I could use a linear combination, so that would work. I could do 2 times 1, 2, 0 minus 1, or plus minus 1, I prefer, time minus 1, 3, 6. Could do that. Or the way I could do it is, like I said, you multiply these together and you add them up. So 1 times 2 plus minus 1 times minus 1, and so on. Just like that. So in both cases, it will give you, of course, the same value. So here you would get the following vector, 3, 1, minus 6. Either way. And last example, which is really important, if I write down a linear system, let's say it's x1 plus 4x2 equals 42, and 8x1 plus 2x2 equals 66. Okay. Now using this matrix vector product, you see this expression here with this, I can put that into a vector. Okay, I can actually write down the left hand side here into the first component of a vector. 8x1 plus 2x2 would be the second component. So I've got this vector, which is equal to that vector. Okay, so I could write my linear system in vector form, and this thing here, I could actually write that as a matrix vector product, just like that. So what I have here is, we'll call that the vector of unknowns, right? So x will be the vector, well, I'm just going to put it in bold. In your book, they're going to be bold. I can do that here. X is a vector of unknown, contains your unknowns x1 and x2. This is what we call the matrix of coefficient. Usually we call that matrix A. Okay, it's important to use a capital letter. Like you may, sometimes it's not always A, but it's always going to be a capital letter. X is not a capital letter. It's a vector, so it's a small x. And on this side, the vector of constants, that's usually vector B. Okay, so this is the vector of constants. And we can do that with any linear system. Okay, so the moral of the story here is that any linear system can be written in the form AX equals B. So from now on, when we're going to talk about linear system, often we'll say, well, consider the linear system AX equals B. Okay, you'll see that a lot. And that's it. I know that was a long video, but we had lots of things to cover before we could actually start doing some exercises. So you'll see that among the first exercises I have to do will be to convert linear systems like this, and we call that the matrix form, right, of the linear system.